Hey everybody, this is Michael from Barton Musical Circuits, and I'm going to walk you through the schematic today for the BMC100 Deluxe Decaying Analog Noise. Right now I've got the full schematic pulled up. This is a big one, so I have broken it down into smaller little chunks. And I'm going to start with the envelope generator right here. Trigger and gate inputs are these two wire pads over here. Both of these are getting connected to this 100K that's going to ground. Trigger goes through this capacitor, which forms a high-pass filter, so we're only going to get a little tiny spike at the start of a gate that goes in there. And then the gate input has a diode going in, so it's only going to pass voltages above 0 volts. And I'm doing that so you could input a LFO that goes +5 to -5 to the gate input, and then you could also input something to the trigger input, and you could use both at the same time if you had, such a rhythmic need to do so. But yeah, both of those go to pin 3 on this op amp, which is wired as a comparator. The threshold is set by these resistors going between ground and +12 volts. So it's just barely above 0 volts. So that way it'll work with triangles or sine shapes, and you won't require like a hard edged waveform to trigger the circuit. So the output of that comparator gets split off to go to two circuits that are almost identical. And these are the two decay generators for the amplitude, which is up here, and the frequency, which is down here. This one's going to get sent to the VCA, and this one's going to get sent to the VCF. And the only difference between the two of these is the value of the capacitor that gets used. The amplitude is a 2.2 UF, and the VCF has a 1 UF capacitor in there. And that's because usually when using it, you would have your VCF cutoff change at usually that's going to be faster than your amplitude because you want to be able to hear that cutoff change. So I found it easier to have that capacitor a little smaller for the frequency. But the way this works, let me zoom in a little bit on it. Whoop, that was zooming out. So when the comparator goes high, that's going to output a high voltage here that the diode will pass on to this 2.2 UF and charge it up to +12 volts. And then once it goes low, the comparator's output will be -12 volts, but that won't pass through the diode because that's a lower voltage than what's on the other side of the diode. And at that point, it'll start to decay the signal. The resistor here, this 1K, is in series with this 1 meg potentiometer, and that lets current discharge from the capacitor down to ground, and we have a waveform that starts to fall down like that. And this all gets buffered by this op amp here that's just wired as a unity gain buffer, and that lights an LED through this 10K resistor, and then gets sent to our envelope outputs through the 2.7K and 2.2K resistors. And it's the same thing for the filter envelope generator as well. That's going to get sent to the VCF, and this one's getting sent to the VCA. So onto the noise generator. This is the noise source that gets used in this module. It's different from the regular decaying analog noises in a pretty big way. The biggest difference is that we have two Zener diodes that we're going to use as our base noise source. So these generate a little bit of thermal noise whenever they're working. Normally you would try to just filter this out when you're using these for a power supply, but here instead we're going to try to actually amplify that noise and use that as like kind of our white noise source. The 3.3 meg resistor is providing a large load to -12 volts, so you should be able to have a pretty large voltage swing, or as large as possible voltage swing that's here at this node where the diode meets the resistor and the capacitor. The voltage here is going to have a large DC change to it, so I have these 0.1 UF capacitors to take that off. At first I didn't think I would need these. I thought that the coming differential amplifier would be able to equalize it out, but I found I got much better response adding the coupling caps in. And the 0.1 UFs, they're attenuating just a tiny bit of bass frequency out of it, You could probably replace these with a larger cap if you needed to have really low frequency noise for this, but I liked the way it sounded with these. But these get sent off to a differential amplifier. This is a form you've maybe seen before if you've been watching these videos of your basic differential amplifier, input resistors that are an equal value, and then a resistor to ground and a feedback resistor that are an equal value. And what this does is it's only going to amplify the difference between its two input sources. So the reason we're doing this is on the old one, the original Decaying Analog Noise, you would sometimes get some sound from the VCF or the sound from the envelope generator, like the clicking on and off of the comparators or the LEDs turning off on and off. You would get that in the noise source because it would couple in through the DC power supply. Because we're adding so much gain to it that these little tiny things that you normally don't notice, they get picked up and amplified by having such amplification from getting our noise. And it would be even worse if you got, sometimes one diode would be a little weak, and it would be even worse by doing that. But by making it differential, any of those little sounds that are going to be coupled in through through our DC power source, all of those sounds should be the same on both of the two inputs because they're both going to get the same clicks from the envelope generator or any frequencies from the VCF. And so this differential amplifier is going to have those cancel out. And all that's going to be left is the noises left between the two, which both of them are going to be creating completely random noise. So that's going to be it'll sound like it's just a single one. They shouldn't cancel each other out with anything other than the stuff we don't want. And so the output of this differential stage that goes up here to this secondary gain stage here, which adds just a tiny bit more gain, but is mostly used here as a voltage limiting stage. So I've used this circuit a few other times where these Zener diodes facing opposite directions are in the feedback path of a gain stage. And so once your output signal goes above 5 volts or below negative 5 volts, the output here is going to then bypass our normal feedback resistor, which sets the gain, and then go straight back to the negative input. And in that way, it's going to turn the volume back down to just being plus minus 5 volts. So it's kind of an automatic clipping circuit that's keeping our volume the same no matter what. And with this, I've built this circuit a few times now, and I've not once had an issue where I had like a Zener that didn't produce enough noise. Like it's a combination of enough gain in the first gain stage and then limiting it in the second one that I haven't had to mess with any resistor values or things like that, or have to test out different Zeners to make sure I was getting a loud enough signal. It's been, a lot more consistent. This is the VCA that we use for the circuit. This is a transistor-based VCA. So here we have our analog input. Now this is going to be normally connected straight to the noise output. The signal from this gets attenuated by this 100K and 470 ohm. So that'll take a plus minus 5 volt input and take it down to like less than a tenth of a volt. And then that gets sent to the base of this transistor here. And we don't want to saturate these transistors. They're pretty sensitive, so that's why we're making it such a small signal. And we're biasing it towards ground by this resistor referencing ground. And then these two transistors here with this 100K resistor, these are being coupled together by having their emitters touched. Or because the emitters are connected, we're creating a kind of a phase inverting system. This is similar to a long tail pair that you would see as in a tube amplifier that gets used for phase inversion a lot of the time. I started out with tube amps before I worked with solid state stuff. But the way this works basically is just as current flows down this way, it's flowing. Current basically is flowing up from these resistors down through the transistors, and the voltage between these 2 points is what's setting how much current is getting pulled through here. And with this, we're actually just grounding it instead of putting a signal in there. And we're just letting the voltage change on the emitter control how much current is flowing through here. And that should be enough to create a mirrored signal coming out of this second resistor. Or second transistor, I should say. One thing we're doing to control that baseline voltage that's between the base and the emitter is we're just changing the DC voltage on the other side of this 10K resistor. So we've got our envelope here. This is our decaying signal, a big thing that goes up to 12 volts and then goes down to 0 volts. That's getting inverted and then also attenuated by this gain stage here. So that'll be, instead of going from up to about 10 volts, it'll be going down to about 2 volts, or down to negative 2 volts at this point. Or this would be like negative 2 here, I should say. So with this, when it's at 0 volts, there'll be no difference between base and emitter, and so no current is going to flow down. And then once this voltage goes down at this point, then you'll start to have some gain as you now have a change in voltage between these 2 points that's getting modulated by the audio signal coming in. And all that is going to create current flowing down here. And these 22K resistors are load resistors that as current flows through them, the voltage difference is going to change on the two sides. The top side is going straight to 12 volts. So we're just going to have a voltage change on these 2 points as the current flows through them. And then these get sent off to another differential amplifier, like I was talking about earlier. And this one, I initially tried it with the coupling caps that I was using in the noise source, but found I didn't need them and sounded good with just the 100K resistors. And then this gets sent to our analog output, this gets sent to our VCA output through the 1K resistor, and this is normalized to the VCF audio input. Next, we've got our VCF control here. So this is the envelope signal coming here, and this is going to an attenuverter. An attenuverter, I can't remember if I've talked about these in these videos before, but you can kind of think of it as being a gain stage that swaps between being an inverting or a non-inverting gain stage. So if this pot here was just going straight to ground like that, this would basically look like a inverting gain stage with a gain of 1, that you would just ignore whatever signal is on this pot because this terminal is grounded. And then if this terminal was going straight up here and just ignoring the pot, then it's got, 0 volts, it's got 0 ohms between the positive input to the input. And so that's so large that you can kind of just ignore this 200K, and it's going to act like a non-inverting gain stage. And then in between, you've got all these other little variables where there's a little bit of signal is inverting and a little's not, and that's going to cancel out. And, straight up the middle, they should cancel each other out equally, and you have 0 volts on the output. And the output of that goes through a 100K resistor, and it meets at this node where that 100K is meeting with these other 200Ks. This is our external control voltage input. And then this is the frequency knob that's setting our baseline frequency. And this just goes from plus 12 volts to ground. And then these are all going to this negative voltage input on this op amp here. And the positive is grounded, so you would recognize this as being like a inverting gain stage, with the difference being instead of having our resistor connecting here like it normally would, we are connecting it down here. The voltage output of the op amp is actually controlling the current flow through this PNP transistor here. We've also got this diode, and that's just providing polarity control to make sure that it's always going to be like a negative voltage, never a positive voltage on the output. But yeah, we're monitoring how much current how much current is flowing through there and linearizing it with this 82K resistor. But this is providing a current to LM13700s that we're using in the audio part of the VCF, which brings us to the audio of the VCF. So our pin 1 and pin 16 here, those are both connected to that control current. from the control section. And then our input here, this is normalized to the VCA output, which I do it that way. I think I mentioned this in another video, but I do it that way so you can just have a single input signal and a single output signal without having to patch between VCF and VCA, and you're still able to pick which of the outputs from the VCF you'd want to use. Feel free to normalize this however you want when you actually build it, because that stuff's not on the PC board, it's just on the jacks. But yeah, our input comes here. It's got a ground reference resistor with the 100K, and then it is going into this first op-amp stage. This is a state variable filter, which is a filter that has a couple of different feedback loops into it. So it's a little difficult to describe what it's doing in stages because all the stages are kind of playing into each other. But our input signal is getting mixed with our bandpass signal here through this resonance pot. And then that is getting differentiated with the low pass signal that's coming from this 10K. You can see that connects way back here to the low pass output. And this is, similar to like a differential amplifier section, that this is going to the negative, this is going to the positive. And from this, we derive our high pass output. So you can imagine this as being all the frequency range here, and then you cut out all of the band pass and all of the low pass. You'd be left with just the high pass here. And so that's how we're getting a high pass output from a filter that is just made out of low pass poles. I'll also say that state variable filters to me are still a little bit magic. I'm going to explain what I know, but there are better people to explain how you're getting all these different poles from one filter. But yeah, this output gets attenuated by 100K and 470 ohm, which is similar to what we saw on the transistor input for the VCA, that we just don't want to saturate those transistors that are on the input of the LM13700. And the 13700 has so much gain also that this is going to basically act as our resistor and as like an amplifier in a low pass filter. Normally a low pass filter is a resistor going to a capacitor to ground like that. But with this, the resistor gets replaced by this OTA here. And so the more current we're pumping into this control pin, the more current it's able to push to the output. And the more current it's pushing out, the faster this capacitor is going to charge up or discharge, depending on which way it's flowing. And that's going to change the frequency response. So when it's not pushing much current, that capacitor is going to very slowly charge up and down, and that's a lower frequency for your low pass filter, and vice versa. That's getting buffered by, these are on-chip buffers built into the LM13700. This is like a transistor in there. And I'm biasing that to the negative 12 volts through a 4.7K resistor. And this forms our bandpass output. You can kind of think of low passing an inverted high pass stage being a bandpass. Which I guess I didn't mention that this was an inverting stage. We were going into our negative input here. The positive input is grounded. And so when this output from the bandpass is getting sent back here through the resonance pot, it is a negative version of the signal from here. So this is actually negative feedback that's getting sent back, even though it's going to a positive terminal on that op-amp. And then we have another stage that works exactly the same, of 100K to 470 ohm going into a negative terminal with a 560 picofarad cap. This second one forms our low pass filter, which this goes through a 1K resistor, like I mentioned earlier. And that's all the parts of this circuit. If you wanted to mess with the resonance, like I mentioned, this was negative feedback here. So we're actually providing less negative feedback when we're turning up the resonance. So if you wanted to have even more resonance to this, changing this 2.2K to like a 1, that's one way to do it. And similarly, if you wanted it to always be a little more resonant, you could replace this 22K with like a 33K or a 47 or something like that. I don't know why I keep trying to draw numbers with this thing. It never works. Let me go through and see what else. VCF controls. These resistors here, these would be easy ones to adjust if you wanted to have the different controls work differently. The frequency depth from the attenuator, that's one that can get a little extreme sometimes. So going up to 120K or something there might be a nice little fine tuning thing if you wanted to tune this thing to your helping. And then also our CV control here has no attenuator to it. So if you kind of knew what signal you would mostly be using with this, you could fine tune that to be one that sounds good with that signal. On the VCA, I don't know if there's anything really. If you wanted to make it AC coupled, you could add a coupling capacitor there. I'd probably use a 10 UF and have the, I'm not sure which side you'd really want to have be the positive. I don't think it really matters. Probably positive the output, negative the input. Noise source, replacing the 0.1 UFs with bigger caps or smaller caps would affect the sound. You could also, if you wanted to filter it a little bit more, you could add a cap here. You could lift up this side of the 10K and then put another 0.1 cap there, or something else. If you wanted to accentuate more of the high frequencies of the noise, you could filter it there. And then also, if you wanted to cut out for high frequencies, you could put a cap parallel to this 47K. On the envelopes, you could change these 2.2 and 1 UF caps to smaller or larger caps if you wanted to get longer or shorter envelopes. The 1K resistors that are in series with the decay knobs, those could be increased to increase the minimum decay time. I wouldn't really decrease them too much, because then you can have a situation where it affects how these caps charge, and you'll start to have envelopes that are like way too small and won't do anything. And obviously the 10K resistors coming off that are going to the LEDs, those are controlling the brightness of the LED. So changing a 10K to a 1K will make it much brighter. I've started using larger values just to try to conserve current. And then if for some reason you had this triggering when you didn't want it to, there was like accidentally triggering off of signals, this 1K could be turned into a 10K. I'm actually drawing legible letters. That's great. And that would raise the threshold voltage up, and it would require a larger signal to turn the envelope generator on. And thank you very much for watching. I hope this helps people build, and I hope it was informative. Have a great night.